All right, we are looking at atomic theory, and we're going to dive in to the quantum mechanical model in a lot of depth today. Now, this concept is a little bit out there. It's it can be a little bit confusing. So, what I'm going to suggest you do is you print out the slides, follow along, and write down any of my kind of analogies to help you understand the content. The other thing is within your slide deck, there are some videos, and I'm going to probably prompt you to pause this lesson and open those videos in a different browser tab and watch those as to get a better understanding of each of the theories as we move along. Okay. Now, we've talked a little tiny bit about the quantum mechanical model in 3U, but I didn't call it that. So some of this is not unfamiliar. But we're going to kind of go back a little bit about what we kind of learned about the atom last year with Bohr and different colors of light and things. So before we do that, though, I want to recap that before the 19th century, experimental evidence really indicated that light has wave-like characteristics, right? So light travels as a wave like this. Now, the electromagnetic spectrum is what represents an entire range of energy that travels like a wave. This is our electromagnetic spectrum, and we talked about this electromagnetic spectrum last year in 3U. And part of our discussions were that if the wavelength, so from the top of one crest to the top of the next crest, that's a full wavelength. If it's longer, it has a little bit amount of energy, and if it's shorter, it has a lot more energy. The part of the electromagnetic spectrum that we can see is the visible light range. It's right in here. And we have our colors, Roy G. Biv. Red has a much longer wavelength, so lower amount of energy. And the wavelengths get shorter as we travel through the visible light spectrum to our violet. Now, all of the waves in the electromagnetic spectrum travel at the same speed, 3.0 times 10 to the 8. Now, it says -8 here. You need to fix this because that is wrong. Meters per second. So this is the speed of light in a vacuum. Very quick. Now, something that we haven't talked about before that I want to point out to you is that the amplitude, so this is the difference between this black line and the height of the crest of the wave, represents intensity. So if it's a high amplitude, the light's going to be a lot brighter or a lot more intense compared to something with a shorter amplitude. Now, both of these pictures are showing wavelengths of the same length, but the one that's got a higher crest here has got a brighter light. Now, at the end of the 19th century, scientists believed that matter and energy are two very distinct, separate things. In fact, we've taught you this like my son in grade 3 has learned the difference between matter and energy. Matter is something that we're regarding as consisting of particles, something that takes up space, has a mass, has a volume. And energy was always described as being in the form of light and described as a wave, saying that it does not have a mass, it does not take up space. And the other thing is that it was always assumed that energy could be transferred in any quantity. So you could transfer any value of any amount of energy that you wanted. Just like if you could spend any amount of money that you wanted. At one point you could spend a half penny. There was a half penny coin. Now, this is actually discovered to not be true. Again, something we taught you in grade 9, we're telling you in grade 12, not right. So matter and energy used to be considered very distinct things, but now they're finding that they actually have some very similar characteristics. Along comes Planck. Now, Planck has his hypothesis that energy instead of being given off as a continuous wave, so something like this continuous wave just continues to go, keeps going, it keeps going, it keeps going, it's actually given off in little packets or quanta. So it's these packets are just little amounts of energy being released. And they call this packet a photon. So what I want you to think about is stoplights. In some intersections, there's a stoplight and the red light is continuously on. So that would be like a continuous wave of energy being released. But sometimes you get to an intersection and it's one of those flashing red lights. That would be something like a packet. It's releasing little bits of energy. Okay. So this is important for a lot of things, and we're going to talk about it. We're going to kind of refer back to this in a little while. Now, they said that the energy that this little photon or packet has depends on the wavelength. Again, so it's still new, something that we already know. We already know amount of energy depends on the wavelength. A longer wavelength in the packet, lower energy photon. Shorter wavelength, the photon has a higher energy. So that's not new. And he did some math and showed like all these equations that are relating speed of light to frequency and wavelength, amount of energy, and there's a constant in there. And honestly, for this course right now, we are not going to concern ourselves too much with this math, with these mathematical relationships. But if you're continuing into science, into physics or chemistry, then you might come across this in the future and you might be using this information. Now, Planck he worked with Einstein, and what they did is developed the quantum theory of light. It's this idea that light should be thought of as a stream of particles of energy called photons. So it's not just a wavelength continuing going, but it's a stream of photons being released, just like that blinking stoplight. They said that all these photons have a specific amount of energy, which is quantized. That's what the word quantized means. It means that they just have a specific amount of energy. And that this light behaves as a wave and a particle. And this is big because they always assumed particles and waves were very, very, very separate. Now, before we continue going into looking at this wave versus particle business, we need to recap what we know about the Bohr atom. And though this is all stuff we looked at in a lot more detail in 3U. So the first thing is that Bohr's the guy who figured out that different atoms release different colors of light and why they did that. And one of the things we looked at is that when an atom absorbs energy, they emit visible light. So our atom here in our picture is in ground state. We have our electron here, and the atom is going to absorb some energy. And what happens is the electron jumps into an excited state. When the atom releases the energy as light, or some of it as light, the electron falls back down to ground state. Now, he used the fact that atoms release energy in the form of light. They produce a different or very specific line spectrum. So when you looked at hydrogen, we see the line spectrum at the top of this image, and then mercury has a very different line spectrum, and so is neon. And in fact, every single atom that you look at is going to have a unique line spectrum. And this was important for Bohr's theory. Now, Bohr reasoned that if atoms were releasing quantized energy, so specific wavelengths, then the energy of the electron must also be quantized. He said because atoms with different amounts of electrons are releasing different amounts of energy, then the electron has to carry a specific amount of energy. That's what quantized means. And he comes up with the first quantum model. And this first quantum model basically describes the behavior of electrons in an atom in terms of their specific quantities of energy. So Bohr found that, and this isn't new to us, we know this already, that electrons remain in the lowest possible energy level, or ground state. Electrons can move to a higher energy level when they gain enough energy. Now, it has to be the exact amount of energy needed. They can't jump up and have extra energy. They can't jump up and have just not quite enough energy. They have to have exact amount of energy to get moved into the next energy level. And electrons cannot be found between energy levels. So they have to be in a specific energy level. And to get into the energy levels, they have to have the exact amount of energy needed to get there. It's like if you go to a concert and you have concert tickets, you can't get to the floor seats if you have tickets for the 300s. You can only go where you have a ticket for. The electron can only go in the energy level it has the exact amount of energy for. Now, he also said that electrons only emit light when they release that packet of energy. So they only emit light when they release a little packet of energy. They're not releasing a continuous wave, just little packets. And we know this from last year, each energy level jump produces a different frequency of light. So basically, this means that light and energy can behave like a particle. The electrons can release little packets of energy that are kind of like a particle. It's really important. This is a really important idea because it explains why electrons don't just attract into the positively charged nucleus. The electrons are spinning around the nucleus so fast, it's that speed that keeps them from being attracted into the positively charged nucleus. Because they are not releasing energy continuously as a wave, they maintain that really high energy that allows them to continuously rotate around the nucleus. That's just right here, right? So they don't release that wavelength as a continuous wave of energy, but only specific amounts when they change energy levels. And then Bohr also said that electrons orbit at specific distances from the nucleus, and while they're in orbit, their energy remains the same. Okay, so that brings us to basically Bohr's quantum model of the atom, where he used mathematical formula to determine the maximum number of electrons that can be placed in an energy level. And we're going to talk a little bit more about what happens next in part 2. If you're confused, which you probably are, I would watch some of those videos that I've posted into your slide deck and in your HyperDoc. We're going to keep going in part 2.